Welcome to this module. Here, we'll focus on sport clothing designed for cold weather protection. Increasingly, professional athletes and amateurs alike venture into harsher and more hostile environmental conditions. As homeothermic organisms, humans strive to maintain a constant core body temperature. This means that heat produced by our bodies must balance the heat lost to the environment. As we saw in the module about energy balance, this constant dynamic is governed by various heat transfer mechanisms: conduction, convection, radiation, and evaporation. In cold conditions, one of the most critical factors influencing comfort and safety is the body's moisture production and its transport through clothing layers. The condensation of water vapor within clothing and its accumulation significantly compromise thermal insulation, as the thermal conductivity of water is approximately 25 times higher than that of air. The human body produces moisture through two primary means: insensible perspiration, that is the continuous diffusions of water vapor through the skin, and sensible perspiration, or liquid sweat produced by the sweat glands. It is important to note that sweat production doesn't always synchronize perfectly with physical activity. The onset of sweating often occurs with a delay after muscle activity increases and core body temperature. The other way around, sweating can persist even after muscle activity has finished. This delay can be particularly dangerous during intermittent sports activity in the cold, such as hiking or skiing in the mountain. If clothing becomes saturated with sweat, it can increase the risk of hypothermia. Wind is another major factor, causing local skin cooling and leading to the wind chill effect. A wind chill temperature can be empirically defined as the temperature that would produce the same cooling sensation at a reference wind speed. Crucially, wind can penetrate permeable clothing, increasing convective heat loss within the garment. Therefore, even if the intrinsic clothing insulation is theoretically sufficient, its effective thermal insulation in windy conditions will be reduced, potentially leading to significant cost stress. Air is one of the best insulators. Therefore, the primary goal of clothing designed for cold protection is to entrap as much air as possible within and between different garment layers, while simultaneously preventing air movement and heat exchange between these trapped air pockets. The most common and effective concept in cold weather sports clothing is the multi-layer system, typically involving 3 or 4 distinct layers. This system usually consists of a skin-friendly base layer designed to manage moisture directly from the skin, 1 or 2 middle layers whose primary function is to provide thermal insulation by trapping warm air, an outer shell which acts as a protective barrier against environmental elements like wind and precipitation. One key method for this is the sweating guarded hot plate test. It is a method for measuring the thermal resistance of individual fabric. It involves placing a fabric over a metal plate heated to a constant temperature within a controlled climatic chamber. By measuring the electrical power needed to maintain the plate's temperature, the calculation of thermal resistance is performed. However, for assessing the thermal resistance of undergarments, such as base layer or mid layers that lie between the skin and another outer layer, this method is less appropriate. In these specific scenarios, thermal conduction becomes the dominant heat transfer mechanism between the layers. For this purpose, the ISO 50851 and ISO 50852 standards are used. In these methods, the fabric is placed directly between two plates, maintained at different temperatures, and the conductive heat flow is measured. The base layer, worn directly next to the skin perform two critical functions. It must be skin-friendly and it must effectively wick sweat away from the body, ensuring rapid drying. Skin friendliness refers to the absence of uncomfortable sensation when the fabric is in contact with the skin. Our skin's sensorial comfort is based on thermal and mechanical perception. Skin friendliness is tightly linked to wettedness perception. The perception of humidity on the skin is in fact an interplay of temperature and mechanical sensation. The perception of the humidity on the skin also depends on the material. For instance, studies have shown differentiation in humidity levels with cotton, but not with polyester or synthetic blends. Moving beyond the base layer, the purpose of mid-layer is to provide additional thermal insulation. Modern mid-layers are frequently crafted from fleece materials, highly known for their excellent air entrapment properties. The effectiveness of these materials comes from their thermal conductivity, which is remarkably close to that of steel air. Typically 0.03 or 0.04 watt per meters Kelvin for fleece compared to 0.026 watt per meters Kelvin for air. While conduction is the dominant heat transfer mechanism, it is important to consider exception. Materials with very low density, such as spacer fabrics, allow for a significant radiant and convective heat transfer. This means that a spacer fabric mid-layer contributes more to overall insulation in a non-convective environment, but its contribution is the lowest under forced convective condition. The outer shell serves as the interface between the wearer and the environment, providing protection against rain, snow, and wind. All the requirements are met by waterproof, windproof, and breathable fabrics, WBFS. These materials typically achieve their properties through either a microporous structure and a hydrophobic structure, or a combination of both technologies. It is important to recognize that waterproofness and breathability are contradictory requirements, needing a careful compromise between optimal protection and user comfort, usually achieved by adapting the porosity and thickness of these WBF layers. Microporous structures are characterized by pores that are large enough to allow individual water vapor molecules to pass through, yet small enough to be impermeable to larger liquid water droplets. These structures can be engineered in various means, including tightly woven fabric, microporous membranes, coatings, and advanced electrospan structure. The transport of water vapor in this microporous system is fundamentally a diffusion process. In contrast, hydrophobic membranes or coating are typically non-porous polymer structure. Here, water vapor transport occurs due to a different mechanism. Water molecules are first absorbed onto the surface, and then they are moved along the hydrogen groups within the polymer chains. These specialized membranes and coating are typically very thin, ranging from 10 to 30 micrometers. Consequently, they cannot stand alone as an outer shell and are usually laminated onto a more robust carrier materials. The WBF layer, by its nature of providing weather protection, often has the highest water vapor resistance within a multi-layer clothing system. This characteristic, while crucial for protection, introduced a significant risk of condensation formation at the inner surface in the cold and rainy condition. The higher the water vapor resistance, the greater the condensation risk. Furthermore, in rainy conditions, the overall water vapor permeability of the garment can be impaired if the outer shell itself absorbs water. For this critical reason, it is common that the outer shell layer is treated with a durable water-repellent finish, which helps prevent two-phase fabric from wetting out and thus maintains the membrane's breathability. With this, we conclude our module on apparel for cold climates. In the next module, we will talk about running economy and running footwear materials.